like we're saying the same thing a bunch of different ways. And so being able to look at like G of 2 and realize like, oh, they're just asking me for a Y value is important, so that we can just go back and forth between all these different ways of saying things, because it's always asked in a different way, right? Depending on what information you're starting with. Like if you're starting with a formula, if you're starting with a graph, if you're starting with like a situation, like you want to be able to move through all of those, like regardless of how we say it. So we could also ask, what if I said, where is G, well, I don't want to say that. I'll say, for what values is G of X equal to, let's do 250. So what did I give you? Did I give you an X value, or did I give you a Y value? Remember the air conditioner is loud. Y, yes. So I gave you a Y value, right? Because if I'd given you an X value, it would be right there. So like I definitely didn't give you a number for X, because in the space of X, we have a variable. So that's us saying we don't know what X is. But remember that G of X is the output of the function G, which is a Y value. So if I find the Y value of 250, the X value that correlates to that is 6. And so X is equal to 6. Right? So that's the same as saying that F of 6 equals 250. Does that make sense? You guys are staring at me like maybe I'm an alien.
I just understood it. So
you got it? Okay. So back to our graph of 2x squared minus 9. Go ahead and write, just to practice this notation, go ahead and write this point the same way I did that other one. So using function notation for your Y value. So the X value of this point is 2. What's the Y value? F of 2, very good. And in this case, we know, of course, it's also -1. But just using that function notation is just something we want to get comfortable with. So try to think about the answer to this without actually doing any calculations first, and then we'll like figure it out. But so let's find the net change in F from X equals -2 to 2. What should that be? So yeah, like we can write it out in function notation. It's true, like we're doing F of 2 minus F of -2. What should we end up with, though? Can you tell just by looking at the graph? It's going to be 0, right? Because remember that the net change is the change in the Y value when you move from one point to the other. And these 2 points have the same Y value, right? And so the output of our function doesn't change at all between these 2 points. Like we know stuff goes on in between, but remember net change only tells us from beginning to end. It doesn't tell us anything about what's going on in between. And so you guys are right. Like the notation on this is F of 2 minus F of -2. And then we can see, like, that's just -1 minus -1 equals 0. Be really careful not to subtract X values, right? So you sort of want to think of it in, like, remember that there's kind of 2 dimensions here, right? We're saying there's a change in our X value, but what we're looking for is how the Y value changes, right? Which isn't necessarily the same. Otherwise, every rectangle would be a square. So let's evaluate f of negative x. So yesterday we plugged in a bunch of like numbers to our functions, but we didn't do a whole lot with other variables or other expressions, so we're going to do a few of those today. Remember that if I evaluate for negative x, that's just saying replace my input with negative x. So my function says f of whatever my input is going to be equal to 2 times whatever that input is squared minus 9. And then I'm evaluating for a negative x here, so that means I have to put a negative x there as well. So whatever is in those parentheses on the left side, I'm replacing my input with on the right side.
We'll just flip the graph over.
So we're not creating a new function. We're just evaluating this function for a different x value. So this is like saying what happens if you plug negative 2 in instead of positive 2. But the graph of the function itself is the same because we haven't changed what the rule is, which is what defines what the graph looks like. We're just putting a different input in. So what do you get when you square negative x? X squared, right? So negative x times negative x, that's a negative times a negative, which is a positive. And then x times x is x squared. So we actually end up with f of negative x equals 2x squared minus 9, which means that the output of f of negative x is exactly the same as the output of f of x. What that tells us is that if you plug negative 2 in, you will get the same exact thing as if you plug 2 in. If you plug negative 5 in, you will get the same exact thing as if you plug positive 5 in, because it doesn't change the formula to change the sign on the input. And we see that in the graph like all over the place, right? These 2 points have opposite x values and the same y value. These 2 points have opposite x values and the same y value. So we see that all the way up. That's why this graph looks the way it does, is because you get the same output from squaring the opposite of a number as you got from squaring the number itself. And that's why every x squared graph has this same general shape. Like there's some shifting around you can do, but in general, because of this property, we will always end up turning around and like repeating our y values again on the other side. Any questions about this guy before we talk about the constant function? Okay, so we're not going to do a whole lot of interesting stuff with the constant function, but we do want to remember, so we talked about this a little bit yesterday, that because on the right side, this is where my rule is. That rule doesn't tell me to do anything with my input. It just says that my output is 6, right? And so regardless of what my input is, it's so tempting to try to do something with your x values, but regardless of what my x values are, my output is always just going to be 6. And so this ends up giving me 1, 2, 3, 4, 5, 6. Whoa, that's not very good. Just a horizontal line at a height. Is that the biggest challenge? Seems to be counting. So it's just a horizontal line at a height of 6, right? We can plot the points that I put in here, right? They're here, here, and here. But remember that when we say f of x equals 6, we're giving an output, right? Because f of x is an output, so we're giving y values, not x values. So it's a horizontal line, not a vertical line. I don't think I saw any vertical lines walking around. There were a couple in the last class. You guys feel good about this? What's the net change between any 2 points on the constant function? It's 0, right? Remember, net change is the difference in the height of 2 points. So if all these points are on a horizontal line, no matter which 2 points I pick, the net change in the function is always going to be 0 because my height's not changing at all, ever. Okay, so this one, because it's x to the third, you can kind of get away with doing this one either way, but I want to make sure to talk about having that negative out front, because if this was x squared or x to the fourth, then it does affect the answers where you put the negative. So when we have a negative x to the third like that, what that's saying is, it's not saying that we're going to take the opposite of negative 2 and then cube it. It's saying that you want to cube negative 2 first and then take the opposite of that. So it's like negative 1 times x to the third. So that negative is happening after the exponent, not before it. If I wanted to change the sign on my x value first, I would have to do that. And again, the numbers that you got on this, if you did that backwards, like, you will get the same number because it's the exponent is 3. But if the exponent was 2, then it would change the signs. So the points we got here, let's see, we got this one, this one, this one, this one. And that one. And like when I draw like x cubed graphs, I sort of think of it just like the parabola we just did for x squared, but like with one side flipped down. So you can kind of do like a curve this way and then like a curve that way. So this guy looks like this and then goes down. Whoa, I didn't go through my points. Down like this. You guys doing okay? Like if your graphs don't look like my graphs, definitely like ask. But we feel good? We can. I mean, we can. It's not going to make it cooler, but we can open it if you want. Sure. You want to help us out, Patrick? It is. I agree. It's very stuffy in here. We usually close it just to keep the cold air in, but it feels like there's no cold air coming out of those things, right?
How big it is, yeah.
It's like they're about to give up. They're like, no, it's just too much. Okay, only a few more minutes, guys. It always cools down eventually in Montana. We should relish it while we have the chance. Okay, let's do a couple things with this guy. Actually, no, let's not. I'm going to use a different one. I think I changed this one to H, didn't I? Okay, so the graph of the absolute value function. Remember, absolute value is the distance from 0 on the number line. So the absolute value of -2 and +2 is exactly the same thing because both of them are 2 units away from 0. So it's kind of like thinking of like walking from one number to another, like without thinking about what direction you're going, right? So we're just measuring distance, which is always a positive number. And so when we do 6 minus the absolute value of -2, we're really just doing 6 minus 2. And that's why we get 4. And that behavior, or that fact, the fact that we get the same thing if we put -2 and +2 in, is going to do kind of the same thing it did with the parabola, right? It's going to make the graph turn around. So this guy looks like... something like this. So the absolute value function is always 2 straight lines put together into a V or an A shape. And like I said earlier, it's the only graph that has straight lines in it that is not itself a line. So every other graph that you draw is going to be a smooth curve, like I said. And that's just like, it's important when we get to calculus because you can't take the derivative of a function unless it's smooth. And so it's nice to be able to look at a graph and know if it's differentiable or not. So if you can take the derivative of it or not, just by noting if it's smooth or not. That's the only reason we really care a whole bunch about that, and why teachers make a big deal about, like, there shouldn't be any, it's a U, not a V. That's what I always tell people, is it's a U, not a V. Okay, let's do a different function altogether. Like, I didn't really want to erase that. That's your homework. Do you guys feel good about graphing?
Yeah.
being able to do it and read it a little bit? Okay. So let f of x equal 3x plus 5. You guys know what the graph of this would look like just in general? Yeah, this is a straight line, so you can always tell a function is linear. And we will talk a lot more about properties of linear functions next week, but you can always tell a function is linear if there's like no exponent on the variable, right? So there's just an x, there's no x squared, x to the third, x to the fourth, or like square roots or funky things like that. So we're going to evaluate, we're going to start with, let's find f of x plus h. This is the reason I was having a fit about the h earlier, but then I chose a different function anyways. But h is not the name of a function here, it's just another variable. What is f of x? It's 3x plus 5, right? And notice that h isn't part of my input, right? The input is always in the parentheses right here. And so my input is still x. Anything that happens now outside of that f of x is just like getting tagged on at the end of whatever I did to get f of x. So this is going to be equal to whatever f of x is, in this case 3x plus 5. So this is my f of x. And then it tells me add h onto that. So I'm just doing plus h. So this is one of those ones that kind of looks like it might be complicated, but it's really like copy what f of x is and then tag an h on at the end, because the h isn't part of the input, so it doesn't affect what happens with our rule at all. It's just we say we're acting on the output of the function rather than acting on the input of the function, because that plus h happens after we plug x into the function, and then we just add something onto it. So we could also find f of x plus h like so. So in this case, that plus h is in the parentheses, right? So it's part of my input. So my input here is x plus h, which means I have to consider that as I apply my rule. I can't just tag it on to the end, right? So my input is going to be x plus h. So I'm doing 3 times x plus h plus 5. Because my rule says multiply your input by 3 and then add 5. So I take that whole thing in parentheses, multiply it by 3, and add 5. So we end up with f of x plus h equals 3x plus 3h plus 5, which contains some of the same terms as the previous one, but isn't exactly the same thing, right? So you want to be careful to really watch out for like where things or operations are occurring. So here we're acting on the input first by adding h to it and then applying our function, whereas the first time we applied our function to x and then did something to the result. Good? So far so good? You guys are all just melting, huh? I'm sorry. It sucks. So let's find net change next. Find the net change in f from f of, whoa, no. Sorry, getting ahead of myself. From x to x plus h. So I'm going to kind of draw this just so we can see what it is we're doing. I don't really care exactly what the graph looks like. It's something like this, like a straight line. So what we're saying is we have 2 different x values. One of them we're calling x, and one of them we are calling x plus h. and each correlates to a point, right? What would we call, like without plugging anything in, what would we call the y value of this point right here, just using function notation? Say it louder. So that's the second one, yes. So if our x value is just x, sorry, I only have 5 minutes to go. It died. Okay. If the x value of this, my pencil died. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Like 10 seconds will give me like 2 minutes. Okay. It's hard to make it through 3 hours, apparently. Well, they can buy me a new one. Okay. So if the x value of that point is x, then the y value is f of x, right? So it's just the function evaluated for whatever the x value is, which means the y value of that second point, that one's going to be f evaluated for what? X plus h, good. So what we're finding is this change in height. Is it h?
Yeah.
So the change in x is h, for sure. But the change in the y value, again, you want to think of like 2 dimensions going on here. Just because the change in the x value is h doesn't necessarily mean that the change in the y value is h. Because, again, if we were to say that, it would mean that every single rectangle was a square. That every time we have a distance or a length in the horizontal direction, that length is exactly the same in the vertical direction, would mean that we didn't have any rectangles, right? Everything would be a square, the same on every side. And so to find this, we're going to do f of x plus h. Oh, sorry, I was going to write up here. F of x plus h minus f of x. And we have to be just super careful not to subtract the x values, right? So this is saying we are evaluating f of x plus h first, then evaluating f of x, and then doing the subtraction on the results. So we have f of x plus h minus f of x equals, and we already figured out what f of x plus h was, right? It is 3x plus 3h plus 5. And f of x, well, they just tell us what f of x is up at the top, right? F of x is just 3x plus 5. And so I'm going to distribute a negative here. Oops. It would help if I actually distributed the negative. So 3x minus 3x is 0. And 5 minus 5 is 0. So we just end up with 3h. So we can see that the change in our y values depends on how much the x value changed, right? Because our x value changed by h, but it's not exactly the same. And this picture we're going to build on like over the next like 10 weeks. But this is the picture that leads us to the definition of what a derivative is in calculus. So we're starting with the net change. We'll build into slope and things like that from there. But this is sort of like the quintessential picture. This whole f of x plus h and f of x thing is kind of like the picture that leads to calculus. So like I said, you don't have to know everything about it yet, but we're just kind of trying to build the groundwork to like build on this idea over the next several weeks. I think that's good enough for today. I'm ready to get out of this room. I gave you guys all your corrections yesterday, so you don't have any more today. I did want to mention, like, there's one